Let's briefly look at a refresher for line angle structures. Remember that we're only showing the framework of the molecule, so we're not writing out the carbons and hydrogen atoms as C and H. We are using ends and bends in the lines in order to represent different carbons. So for example, if we're looking at drawing that has two bends in it and two ends, that represents 4 different carbons. Any bonds that are not drawn contain hydrogens. So because our first carbon only has 1 bond, wants to make 4, that means that there are 3 hydrogens attached to that first carbon. Our second carbon, carbon number 2, has 2 bonds that are drawn to it, which means that it still needs 2, and so it is going to have 2 hydrogen attached to it. Our third carbon again has 2 bonds, which means to make a total of 4 bonds, we need to have 2 additional hydrogens that are not drawn. And our last carbon has only 1 bond drawn to it, 1 line. And so to make a total of 4, we are going to have 3 additional hydrogens attached to it. So our overall formula for this is going to be C4H, and then we have to add up our hydrogens. So C4H10. Okay. If we are drawing branched molecules, okay, where we have additional carbons coming off that backbone chain or that long carbon chain. So we have here, in our second example, we have 1 branch and 2 branches. We also need to include that in our line angle structure. So that first branch comes off 1, 2, 3 carbons. So we have 1, 2, 3 carbons, and then we have the branch that comes off of it. Okay, the second branch is off our 4th carbon, and so we draw another line because it's just 1 carbon. We draw a single line off of the correct carbon in the chain. Okay, so we represent branches with lines that contain the number of carbons in that branch. Please notice how our structure gets to be much cleaner. So instead of drawing all these carbon and hydrogens out, it becomes a much cleaner structure with those branches drawn as line angle. We also have to represent cis and trans appropriately if we have molecules that contain double bonds. So if we look, let's look at our top molecule here in our third example. So if we draw our line, we can see that the carbons coming off that double bond are on opposite sides. So that is a trans molecule. Okay. So when we draw our line angle, we also want it to be trans. So we draw our double bond. The carbons coming off of that double bond are on opposite sides of the double bond. Okay. If we have a cis molecule, if the carbons are coming off the same side of the bond, we also show that in our line angle structure where the carbons are coming off the same side of that double bond. So they are on the same side. So that would be our cis molecule and our trans molecule. If we're drawing triple bonds, our triple bonds remember, we're trying to show the shape of our molecule because a triple bond is linear. When we draw it as line angle, the carbons that are contained in that triple bond need to show that linear structure as well. So where the three lines stop, there is a carbon at each end of that triple bond. Okay, and then an additional carbon at the end of this line that shows the single bond. Okay, so we are representing branches, cis and trans, and the shape of our molecule all in our line angle structure. How about line angle when we have heteroatoms, atoms that are not carbon and hydrogen? Well, we still want to show the bond between the carbon atoms as line angle. So we have a single bond between our carbons. So we have our single bond between our carbons. And then when we show the functional group, we need to put that bond in and show that there is a bond to the element that is not carbon or hydrogen. We also include, because the way the atoms are attached is really important for different functional groups, we also have to show the bonds to any hydrogen atoms that are present. Okay, so this would be an example of ethanol. 2 carbons bonded to an oxygen and a hydrogen. And so this is how we would draw the line angle for ethanol. 2 carbons, we have a bond to our oxygen and a bond to our hydrogen. All right, let's practice. So determine the type of functional group present in each structure as well as the formula of that structure. Pause the video while you determine your answer, and then once you have your answer, start the video and we'll talk about it. Let's start with the first formula on the left. Okay. We have this triangle structure with an oxygen, and if we look back at our infographic and we compare the structure, the oxygen with 2 carbons makes a triangle. This is an epoxide. And epoxides tend to be pretty reactive because of the strained shape of them. Okay, now let's count our carbons. So any end or bend is going to be a carbon. So 1, 2, 3, 4, 5, 6, 7. So we have 7 carbons. Now each carbon wants to make 4 bonds. So if there are not 4 bonds drawn, they are going to be hydrogen. So on our first carbon, there's only 1 bond drawn. So that means there's going to be 3 hydrogen off of that carbon. Our second carbon, there's 2 because we have 2 bonds. Same on the third, 2 hydrogen off of that carbon because there's 2 bonds drawn. When we get to number 4, now there's 4 bonds drawn, which means there are no hydrogens on that carbon. 5, there are 3, so there would be 1 more. 6 and 7 each have 3 hydrogens. The oxygen, if there was any hydrogen attached to it, it would need to be drawn. So if we count up those hydrogens, we have 14. Okay. Any additional element comes after the carbon and hydrogen, so we have 1 oxygen. We do not typically write a subscript if there is only 1 of them. If there would be more than just oxygen, okay, if there's more than 1 different element than carbon and hydrogen, then they go alphabetically in the structure or in the formula that's drawn. Okay, let's look at our second example. So in our second example, we have a carbon at the end of that triple bond attached to a nitrogen. If we look at our infographic and we look for a carbon triple bonded to a nitrogen. This is a nitrile. Okay. So that would be our functional group. If we want to count our carbons, 1, 2, 3, 4, 5, and don't forget the 1 in the triple bond, so that's 6. So we would have C6. Now we have to count our hydrogens. We have 3 off the first carbon, because there's only 1 bond drawn, 2 off the second. The third already has 3 bonds drawn, so we just need 1 off of that one. 4 we need 2, because there's 2 bonds drawn, so we need 2 hydrogens. 5 we need 3. If we look at that 6th carbon, it has a triple bond and a single bond, and so that already has 4 bonds, no additional hydrogen there. Now if we count up our hydrogen, we find that there's 11. We also have a nitrogen. So 11 hydrogen, 1 nitrogen. Our last structure, we now have a carbon, which we can think of as R groups. So carbon on the left side of our oxygen, carbon on the right. So those would be like 2 R groups. That is an ether. Oxygen singly bonded to 2 carbons. If we count our carbons, 1, 2, 3, 4, 5, and we count our hydrogens, so all of these end carbons are going to need 3. Carbon number 3 has 2 bonds, so it needs 2. Carbon number 2 already has, carbon 3 has 2 bonds drawn, it needs 2 hydrogens. Carbon 2 has 3 bonds drawn, so it only needs 1. So this gives us 12 hydrogen and 1 oxygen.